Okay, students, good morning. Is my voice coming? I am audible to you or not? I am audible to you or not? All the students, I am audible. Arjun, Abhishek, yes or no? Is my voice coming? Okay, so we'll wait for 1 or 2 minutes if everyone will join, and then I will start the lecture. Okay, student, let me start the lecture. So, previously, I discussed with you about what is basically the rapid product development and all. Let me have a quick recap, and then I will move toward the another topic today. So, what is there in today's scenario is that the market today, time compression is one of the major factors which adds to the agility of the organization. And time compression means companies who are making the products, they should be very much informed, and they what they will do is uh, they will be having that particular things how they can able to make the time compression, how they can able to kill the time, which will be one of the most important factors that will increase the overall enhancement of the organization or overall progress of the organization. So how that particular things will be coping up. So if you are having a rapid product development, it will enhance these capabilities of the organization and their chances for competition into the market. So how their chances, how the organization will perform in the market, that depends upon the competition. Today I will show one video to you, and that video is very interesting regarding about the design with respect to the additive manufacturing. See, if rapid prototyping is another name is additive manufacturing, where we are having the component which will be made layer by layer. So how you can able to make the component layer by layer? Okay, that is a additive manufacturing process, which will be differs from the subtractive manufacturing process, where we are just subtracting the material or removing the material through the different means like milling or maybe drilling or some other particular purpose. So how accordingly we are designing anything with respect to the additive manufacturing, that particular video will be showing you. But first, the recap. So rapid product development is a synergic integration of various time compression technologies, and which may be virtual or which may be physical in nature. And traditional manufacturing process, what is that? Like, if you are having a manual code, you are having the DFM analysis, where you will do the analysis with respect to the design for manufacturing. You are having the manufacturing attributes, and accordingly you can go for the manual order of any particular things. Then you can make the mold design. You can have the mold manufacturing. Parts are being molded, inspected, and then shipping will be done. That is basically the process of the traditional manufacturing. Now, I told you about the difference between the rapid prototyping and traditional prototyping. Like, process is considered to be additive, and parts are being built up by your adding in horizontal layer process. While if you compare the traditional manufacturing process, it is considered subtractive, where the parts are being built up by removing material from a block of unwanted material. In the rapid manufacturing process, controlled maximum controls of the things are being there by machines and software, and we are having the very less human interaction. While if we compare with the traditional manufacturing process, more human interaction is there and more human expertise is needed. If we compare the rapid manufacturing process, here the models are created faster and that will reduce the time between iterations. While if we compare the traditional manufacturing process, it takes more time. Rapid manufacturing process is cleaner in operation, means you are having less dust and waste. While if you see the conventional manufacturing process, less clean in the process. Okay, if you see the traditional manufacturing process, the material is being subtracted from the specimen, so the material is being removed through the chips. And in the rapid manufacturing process, difficult shapes you can able to build. While if you compare the traditional manufacturing process, it will be only useful for easy and simple shapes. So based on these things, I told you what are the basic prototyping method which will be the best on terms of these particular parameters, traditional or rapid. So shape generating capability, can the materials be formed into the needed geometric features to adequately represent the part? So that in that particular parameter, rapid prototyping is the best. Functional testility and validity, are the material properties representative or scalable? You can able to expand or reduce the size according to your concern, and then you can able to validate it according to your feasibility. That can be easily available in the rapid prototyping method. Fabrication cost, if you compare, then will the prototype that you are making, will that be costly or labor will be acceptable? And if you see the fabrication time, then how long will it take to fabricate the original and one or more duplicates? So these are the basic parameters on which the prototyping method is being made. Now I told you about the pillars for the rapid prototyping, like virtual and testing. Prototyping virtually, how we can able to make any prototype and we can able to test it. In the physical prototyping, we have to make the physical model using the different means like the materials and all, and synergic integration technologies. Virtual prototyping is carried out in virtual or soft environment, and it will save the time and cost. This is an example of the virtual prototyping, like we can make the machine design, electrical design, embedded design and all. And the virtual model, virtual window of that particular model, we can able to test it. Electronic system, this is a car system where you can able to do the analysis. What are the basic advantages of the virtual prototyping is, like you can have the minimum risk to human life, I told you, and you can able to have the upward and downward scalability of time. You can change the time accordingly in the virtual environment, and there will be less fatigue in the process. What are the basic technologies for prototyping? Like is there like geometric modeling, reverse engineering, virtual and augmented reality, finite element analysis, boundary element analysis, motion analysis, tolerance analysis, and design for X. Physical prototyping plays a very important role in the development and analysis of any new product in the industry, like how physically you can make a product and how it will be useful in the industry. And in order to compress the product development cycle time, activities are carried out in the virtual world as far as possible. And when this is no longer possible, they can be done rapidly in the physical world. So what are the basic factors that will be taken care for time compression technique, like material specification, quality and accuracy, cost? The cost of the rapid prototyping part may be much higher than one might by the pattern maker. Okay, the person who is making the pattern, if you see the cost of RT maker, that is one of the disadvantage. Like RP coaster is somewhat costlier, or if we compare with the conventional or numerically controlled machining, and RP can make a pattern faster than the numerically controlled machining process or conventional process. Yes, that is true. Like RP can be able to make the pattern if you compare faster in compared to the numerically controlled machining. And the technologies which will be there in the rapid manufacturing is computer numerically controlled machine, robotics, computer aided process planning, and rapid prototyping and tooling. What are the basic synergic integration technologies that will be there in the rapid prototyping is for innovation, various types of integrated process are carried out and time taken by the activity may be constant or variable. So rapid product development activities are not carried out properly if it is not properly managed. So you need to manage all the activities in a proper way, integrate all the activities with respect to the time in a proper way. Then only you can able to make the things in a proper way with respect to the rapid product development. And so proper managerial skills are very much important for carrying out these activities. So you need to have the activities which you want to take care, you need to carry out with proper management. Otherwise, what will happen is that you cannot able to manage the things in a proper way, and then it will be difficult. So the thing is like you have to you have to manage all the activities of the rapid prototyping in a proper manner. Then based on the technologies, I told you about the concurrent engineering. Like if you are doing a project together, then you need to have the people from all the departments, they are working together on the same project. So all the activities are being carried out by, like, suppose design person is there. So he is also carrying the activity parallelly with the manufacturing person, with the production person and so on. So that is concurrent engineering, which is also a part of the synergic integration technology. Then the product data management, like we are having a data of any particular process, how you can able to manage that particular data. Then e-commerce, electronically, how we are doing the commercial activities. And then you are having, see, students, I have not told you to give the attendance just now. So just give it at the last. I will tell you, I'll give you the time for that. And then you are having the computer integrated manufacturing. Now, there should be a discussion like differences between traditional prototyping and rapid prototyping. Can anybody tell me what is the difference between traditional prototyping and rapid prototyping? Raise your hand, or otherwise I will ask. Jeet, Sagar. Okay, before that, I will just show the video to you. It's a somewhat longer video, but it will give you a more knowledge about how we can able to execute the design for additive manufacturing. See, this is a video of the SolidWorks, and that is being taken in order to tell you like how we can able to carry out the activities for design for additive manufacturing. जैसे डिजाइन फॉर ट्रेडिशनल मैन्युफैक्चरिंग में हम मैन्युफैक्चरिंग एट्रीब्यूट्स लेते हैं, वैसे कैसे हम अगर एडिटिव मैन्युफैक्चरिंग के लिए चीज़ों को डिजाइन करना है तो कैसे करेंगे विद द हेल्प ऑफ द सॉलिड वर्क्स. सॉलिड वर्क्स इज कॉमनली नोन टू एवरीवन, सो जस्ट सी द वीडियो.
Internally, our conversations with customers on this very topic, I think in 2019, it's gone up close to fivefold. There's a lot of interest in this, in designing for additive specifically. A lot of companies are interested in knowing whether their parts are feasible for production in additive manufacturing, or how to incorporate 3D printing into their design to manufacturing process. So this is a great place to start. What a lot of people use 3D printing for is mainly prototyping. And a lot of the news, a lot of the really big, cool looking parts are production level parts where people are using it for end use manufacturing. So first off, again, a lot of people use 3D printing for prototyping. That's form, fit, function, assembly, wondering whether something's going to fit, how is it going to assemble into place. But there's also jigs and fixtures, which is huge. Go, no-go inspection parts. A lot of these need not be made out of metal. You can have a digital inventory and go ahead and print these on an as-needed basis. These are sometimes used for carrying sensitive components from one region to the other. For short production runs, tooling has been great, where these have also gained prominence in the last 5 to 10 years. And lastly, something that gets a lot of publicity is end-use part production. It typically needs a bigger investment up front. A lot of bigger companies relatively gravitate towards this process. But for each of these 4 major categories that you can divide additive manufacturing into, you have these slightly different set of rules that you have to adhere to. So we're going to go ahead and talk about that and then continue on. Okay. So I'm just going to check my notes real quick, and if you guys cannot see my screen yet, or if you don't see a change in the screen, let me know. And once again, there's a questions box on the right. Feel free to enter any questions you have, and I will definitely answer them at the end of the webinar. Okay, continuing on. So the outline for today, we're going to be starting out with talking about orientation considerations. This is something to start out with, relatively basic, and then we'll go into printer constraints. Based on the type of 3D printer you're using, there's going to be a lot of constraints that come in with respect to that. Okay, what are specific constraints to the 3D printer that you're using that you would want to take into account? Okay, continuing on, we have consolidation of multiple parts. This is where you have a multi-part assembly that you're using right now using traditional processes, and then if you're looking to incorporate an additive manufacturing process, you now have the ability to create more complicated parts. So you can consolidate multiple parts into one complicated part that would potentially be lighter, that's easier to manufacture with additive manufacturing. So we'll talk a little bit more about that. Topology optimization, it kind of goes hand in hand with additive manufacturing, where you can now create parts that are a lot more lighter, based on the stiffness of the part, based on where it's going to be used, the loading conditions of it. And lastly, something that's relatively unique to 3D printing is the ability to create ladder structures and have a variable infill. So while there's of course weight savings that can be done with this, there are also some functional use cases that we will talk about. Let's start with orientation. So to start out with, if I have designed a very simple CAD file here, it's just a hook, then I would want to, if I want to 3D print this, I have a couple of different options for orientation, right? Of course, I've just shown 3 potential options, but you can also have it at different angles, right? So this first one, I'm processing this in one of our local printers, would be 38 minutes. The next one, slightly longer, an hour and 34 minutes. And another one is vertically upward, it's almost 2 hours. So speed is one of the major considerations that you would take into account when you want to 3D print a part. But there are a bunch of other considerations as well. One of the most important ones, other than speed, is where you're actually going to use this part. Okay, so you want something that's going to be strong in the direction of usage. So for example, in this hook, you're probably going to be pulling it in this direction downward, and you want continuous strands going through the direction of where the loading is going to be, so that the stresses can be alleviated. For an FDM-like process, of course, some of the machines that we cater with, the FDM process, the PolyJet process through Stratasys, there's desktop metal printers. In the FDM process, you have layer lines that are produced, right? And you have the previous line, and then the next line gets printed. So typically, your part is stronger along the X and the Y, and relatively weaker along the Z direction. Okay, and I do want to say that this is true only for an FDM process. There are some other processes out there where the layer lines are small enough, where you follow a printing process with a sintering process, where you're fusing the material across different layers, in which case the mechanical properties are more isotropic. But in this specific scenario, we do have a relatively weaker mechanical strength in the direction of the build. So keeping that into account, let's go to a slightly more complicated part. And in this case, the little latch mechanism that you have, it's going to go on that little hook on the corner. So we want to make sure that we have good strength as we pull that hook upward. Okay, so if you print it lying down, which would be the fastest way to print it, that would be great in terms of time. But the orientation that you see on the right would be better in terms of giving you strength along the direction where you're going to be pulling that puck over there with the latch mechanism. So long story short, if you get continuous strands of material going through the different areas, especially in the direction where you expect the loading to be, then you're going to get much better mechanical strength against the stresses that this would face. So here's a quick 3D print of that part that I just took into account. We will be talking a little bit more about orientation, but I want to go ahead and talk about printer constraints. So this is relatively important. And the type of printer you use. So a lot of people who are looking to get into additive manufacturing, there are now so many different options out there for what printer to use, right? So every printer is every technology is going to be relatively unique, and based on the type of technology you have, they might have slightly different constraints which you want to take into account. Let's start with draft angle. So if I'm going to compare a 3D printing process to an injection molding process, in injection molding, they tell you to have a little bit of draft so that you can go ahead and pull out the mold, and there's separation with the part itself, which is great. But in a 3D printing case, when you have a draft, what happens is the thickness of your part is going to be relatively different across the different layers because of the draft. This could lead to potentially not having enough contours on the inside. Something that you see in the right of this picture or in the slide is stepping. Stepping is something that you would not be able to avoid. Of course, if you have a smaller layer thickness, then the stepping effects are seen lesser. But with any 3D printing process, because you're printing at one layer at a time, you are almost always going to have stepping effects that you see. Okay, so this is something you definitely want to take into account. If this was printed upside down, then some of these faces would have support material touching it. Again, comparing different types of 3D printers, there are some printers where, imagine you have a part and you shine a light from above. Anything that creates a shadow below is going to need support material below it. Okay, think of your dishwasher where you're trying to align all of your vessels such that they won't collect water, right? Similarly, in a 3D printing, it's the reverse of that. In an FDM-like process, typically most printers have a 40 to 45 degree angle above which the part is going to be self-sustaining. Okay, that means you don't have to remove support or anything like that. So draft angles is important as much as possible. If you have a uniform thickness, it is going to help you in making sure that your parts are uniformly processed and have good strength. If I go into details of the processing of the part, one thing that needs to be looked into is the thickness. And this once again is going to be directly related to the type of printer that you're using. Okay, so let's say you have a fillet as you see on the left. You want to make sure that you adjust the inner and the outer fillet of a relatively thin part so that you don't have this little gap that pops up in the middle, right? If you have this gap pop up in the middle, it's thin enough where you cannot apply another layer of material in there, and then but it's big enough where as you squeeze on that fillet, you're going to find the strength of it is relatively lower than some of the other regions where there's continuous strands of material. On the right, once again, thickness plays a big part. You should, if you know the thickness of your parts, there are tools available to alter the width of the raster that you see right now so that you get a complete fill as compared to a little gap in the middle. If you do have a gap in the middle, those walls are going to be relatively thin. Expanding on this topic a little bit more, so some of the thicknesses, the thickness levels that we have available in the FDM printer is so that 127 millimeters is 5 thousandths of an inch. So I like to think of these, as a good colleague of mine puts it, as different paint brushes. Okay, you won't have a one size fits all for a paintbrush. Think of each of these paintbrushes, and for each paintbrush there is a width for how wide that paintbrush is going to paint. Okay, so similarly for a 5 thousandths of slice height thickness, you have the width of the bead that goes in the XY layer. Okay, so for a 5 thousandths wall slice height, you can you typically want to go about the least you want to go is about 4,000 millimeters in terms of its wall thickness. So there's a default width for each thickness height that you can then take into account. So feel free to look at this table. Again, there's 5,000, 7,000, 10,000, and 13,000s. And of course, there's also 20 thousandths of an inch as your thickness. And for each of them, you have a minimum thickness that you want to stay above so that you get a good strong wall or a good strong design. Speaking of thickness values, once again, the type of printer you consider is going to be dependent on the thickness that you have. So once again, our FDMs go from 20 thou, 13, 10, 7, and 5. And if I go and look at our PolyJet technology, it goes down to about 27 microns and also as low as 14 microns. And to give you some perspective of where this is on the scale, the average sheet of paper is about 4 thousandths of an inch, and then you also have the diameter of the average human hair, which is close to 2.5 or 3 thousandths of an inch. So this gives you some perspective of the size. Okay, but one of the considerations that you want to take into account is the resolution of your print. If you want to print something very big, then if you have a very small resolution, it's going to take exponentially longer to print that file. but you're going to get good resolution. Likewise, if you flip that, if you have a slice height that's very thick, let's say 20 thousandths of an inch, your print is going to be exponentially faster, but the resolution or the detail along small regions may not be as much. So on that same note, another thing you want to consider as you're looking at different printers for manufacturing of additive parts is going to be what is the maximum build volume. Okay, so again, to give you some perspective, the one on the left, 36 by 24 by 36, is an F900 part. The one on the right is something a lot smaller, which is our PolyJet technology, where you're expected to print relatively smaller parts. Okay, I think that one's about 11.5 by 8 by 6. Okay. All right. Continuing on, let's talk about support. Support is again unique to 3D printing, and the earlier you start thinking about support as you additively manufacture your part, the more important, the more beneficial it would be. A lot of technologies have support that you can just throw it in a tank and it dissolves away. And that's great, right? Because you don't have to go and post-process those and manually remove each of those, right? Because then if you have small features, you could potentially break them as well. Some other materials may not, or some other technologies may not have support that automatically comes off through a soluble bath, which means you need to go in and dig through that and remove it yourself, right? That directly potentially affects your design as well, because if you have a region where you just have a thin channel for fluids to go in to then dissolve the part, you could potentially not put in some sort of applier or something to remove the support material yourself. So you need to make sure that the orientation and the design of the part matches your ability to go ahead and remove the support material. So this is one thing that definitely needs consideration. Continuing on, here is another part that I designed without going too much into the functionality of it. I printed this on its side. So this left side was where my build my build bed was. I always had this in mind before I started designing this part, and that's why a lot of these cutouts that you see have 45-degree angles on them, and hence it's going to allow me to print them without having supports below it. So right now the only support I would need is a little bit here and a little bit over here, and I won't need any other support to hold this part up. Typically, again, for some of our printers, to switch from model to support, it takes about 18 seconds on the same layer. So imagine this was a 300 or 400 layer part. That 18 seconds, depending on how many layers you have them, is going to add up. So long story short, if you can design your part to not have support or to have the least amount of support, then you're going to go ahead and have a much faster build. So it's not, and you have the flexibility of having a higher Z direction, which is the other main component that adds to your print time. One more example on support. So on the left, you see a traditional design with unsupported vertical features. And this one specifically has a build time of 2 hours and 2 minutes. Making some slight modifications to the design, on the right, you have a part that takes just 1 hour and 34 minutes. The idea here is that the design changes that you make have 45-degree self-supporting features right below those overhangs, and that way you don't have to have support material below them because the part is supporting itself. So as you design your components, think of these as some of the considerations that you need to take into account. Okay. The next one is material considerations. Based on what mechanical properties you have different types of materials available. Just some of the materials that you see in this picture, you have PC or polycarbonate, you have Ultim 1010, Ultim 9085, you have ASA, ABS, and all of these have varying mechanical properties. Again, we have something like nylon carbon fiber that's extremely stiff. At the same time, we have something like nylon 12 that's very flexible. So based on the type of additive process you're doing, or the final end use part design that you have, make sure that you pick an adequate material that matches those considerations. Just another quick note on materials. This is kind of the fastest developing field inside of additive manufacturing, because that's one of the biggest constraints that people have in adopting additive. So every year there's a lot of new materials coming out, and also the ability to process those materials. What are the optimum parameters to process them? Okay, so continuing on from here, we have inserts and threads. You can see some pictures on the top where we have them printed out. Ideally, I would recommend not printing out threads. If you're using something like an FDM process, threads are relatively small and the amount of detail you need is a lot. If you switch to, let's say, a polyjet-like process, the threads look very nice, but then you don't get the mechanical strength that you need. The picture on the bottom left is one where we've paused the printer and then put in an insert or a nut. And then on the right, you just have the hole that's 3D printed, and then you use a soldering iron to put in an insert by just heating that area up and then just press fitting that insert in. So there's some capabilities to take traditional connectors into account in your 3D printing part. Also, imagine this hole that you have was in the XY plane, or in the XZ or the YZ plane, where you're building perpendicular to that. Typically, if you have a hole, then you need to add support material inside of that and remove the support. One thing that some people do is they drill the hole as a post-processing operation, as compared to having the hole in a 3D printed sense, and that gives them much better resolution as well. All right, there are a few other considerations. So once again, hole sizes. This is something, if you have a relatively small size of hole, I think for an FDM process it's 6 millimeters, then you don't need to add support material inside. It's going to be self-supporting. So that's one thing to keep in mind. If you have multiple prints, because the print that you have is bigger than the build volume, then you would divide the print up with locating features, so you would have to take that into consideration. Color and textures are other big things that people like to replicate in their prototypes or marketing models, materials. That becomes a big part, even to get grip or for ergonomics. So that's something to keep in mind as well. All right, moving on to consolidating multiple parts. Right. So the first thing with doing this is, do you have the design freedom to do this? Right. Again, what we are talking about here is the ability to, let's say you have a 10, 20, 30 part assembly right now. You could potentially consolidate them into fewer parts, but a more complicated part, right? So this involves making major changes to your design, right? And when we say major changes to your design, you're talking about not only modeling them from a CAD perspective again, you're also talking about doing analysis to make sure that the functional use of that part is still true, right? So from a modeling perspective, you can either start from ground up, or you can go ahead and remodel based on what you have right now, right? From an analysis perspective, there is the structural analysis. So a lot of times, typically the high stress concentration regions for an assembly is when you have multiple parts coming into contact with each other. Those are typically, or in a lot of cases, those are the high stress regions. So when you consolidate parts together to create fewer parts, you have less parts in your bill of materials, and you don't have to worry as much about design for assembly. And also some of these high stress regions are accounted for because you now have one continuous part. Just a few examples. So here is one from Optisis, where they created a small micro antenna I think they consolidated about 20 to 30 parts in this case to come up with just one part. Okay, typically these need major design changes, so there is a higher time cost upfront, but then the rewards are going to be much more bigger. And you can see we're going to be talking about lattice structures later on. You can see some lattice structures in here. We're going to be talking about some of the considerations we spoke about before this in terms of the print direction. If you are consolidating parts or designing specifically for additive, you can start taking this into account. Okay, the GE parts are pretty well known, where they consolidated close to 20 pieces down to one in this fuel nozzle. They've supposedly produced 30,000 of these successfully, and it's been operating in the field. When you do this, again, there's a high upfront time cost, but then the lead times and the production times greatly get reduced. Also, there's no design for assembly. So one more example to talk about here. In this case on the left, you had 18 different individual parts that was brought down to just one part. So from a modeling perspective, when you're doing this, I would recommend switching to a multi-part mode as compared to being in an assembly. So we use a lot of SolidWorks here at Go Engineer, and it really helps us to work in a multi-body or in a single part multi-body mode as compared to a multi-part assembly level, because that gives me a couple of added functionalities in terms of not having to worry about the parts moving out and not having to constrain them with mates. And it also lets me extract surfaces from multiple different parts to then create my new one part. So if this is something you're interested in, let me know, and I will be more than happy to kind of talk more about it. Topology optimization. Okay, this is a field that I specialize in. This is something I did part of my research on, and it's an amazing technology. If you haven't heard about this before, just a brief synopsis. What topology optimization does is you take your existing design. You typically want to maximize the design space or the space that your design can occupy. And what you're doing is you're specifying the loads and the boundary conditions that act on your design. And then you're using an algorithm based, or you're letting the computer decide which regions of your model contribute the most to the stiffness of your design based on that specific loading and fixture condition. And of course, you're taking materials as well. So this is similar to a finite element analysis method, where you go ahead and mesh the part up and go ahead and define your boundary conditions, and then based on your initial design, it's going to discard away regions that are not important. Okay. Last year I did a couple of webinars on this topic. I'm going to be so if you Google these names, you should see those webinars. But we're going to be posting this video on YouTube, and when I do that, I'm going to have links on these specific spaces for those webinars. So if you can't find it, look for this webinar in maybe a week or so, and you will see additional links to that one. To go through a brief process of what topology optimization is. So this is a colleague of mine, Wes. It's his truck, and you see that little landing place on the bottom right. So we went ahead and looked at that, and we created a CAD model out of that. So here is what it initially looks like, and I went ahead and created a simplified CAD model. And the way topology optimization works is you then take this CAD model and go ahead and define regions where you're going to apply fixtures, loads, and regions that you want to allow the software to go ahead and remove material from. So here is my initial shape. I go ahead and describe some of the regions that are fixed. I go ahead and specify the loading conditions. So imagine someone stepping on the place where you see the arrows for the load. We have some constraints on the type of shape we want. And finally, there's your initial design, and topology optimization spits out a result something like this. That's potentially lighter in weight and is more efficient because it's more stiff, based on where it's placing that material. You can go ahead and create a final design based off of this. There's a lot of research done on going from topology results to a final shape. And then from there, we can go ahead and 3D print a final part. Okay, so this one I printed out of Altum. Typically, if I'm expecting a lot of stress on a part, I'm going for something that's relatively stiffer, like nylon carbon fiber or Antero or Altum. Let's also lastly talk about lattice structures and infills. Okay, one thing unique to 3D printers is the ability to create lattice structures and infills where you don't need the part on the inside to be filled 100%. Okay, this is unique to 3D printing and some very high-end manufacturing processes like open cell phones and things like that. This produces weight savings without having to do a lot of work from a design perspective. Okay, it's easy to implement. It reduces the stiffness of the part. So something that you see on the left, the GE bracket is very famous, right? But in this case, we made it even lighter than a topology optimization by adding a variable lattice structure on the inside, such that regions that are high stressed, like the one in the center where you see some of the red colors over here, have a solid build, but then there are other regions that are relatively lower stressed, where you have a lattice to reduce the amount of material. Something on the right, like an implant, this is a hip implant. While reducing the weight is useful, there's another functional purpose here, which is osseointegration. The more pores or the higher surface area you have, the better the possibility of both.
Okay, students, so you have seen in the video, uh, small portion is left because time is running up, so I am just concluding it. Design for manufacturing refers to like how you can able to carry out the manufacturing for making the rapid prototyping process, and the rapid prototyping process will be carried out in a layer by layer manner. So how you can able to select the appropriate material, how you can able to do the optimization, how you have to select the latex, all these things has been beautifully understandable in this particular video. So that is why my particular purpose to show this video is to you, sir, just to make you understand like how the manufacturing, so the addition, the design for the additive manufacturing will take place. So we'll carry out in the next lecture also this. So all the students give your attendance quickly and you can leave the meeting. When you give your attendance, you can leave the meeting. Quickly give your attendance. All those who have not given the attendance, quickly give it. Venkatesh, if you have not given your attendance, you can give it. Otherwise, I am going to end the meeting. Okay, if everybody has given the attendance, I am going to end the meeting. Thank you.